So like I said, we'll be relying on the Inside Stats videos. I think they do a better job explaining this stuff than the book does. But the book, it kind of gives you the theory, the background. And then Inside Stats gives you the application. All right, let's bring this over here and share screen. So like I said, we're talking about sampling distributions and sampling statistics today. And what that means is we have sampling statistics, and this is the statistics of a sample. So when we say statistics, we're usually talking about a sample of some observations, some amount of observations. And basically, we're just talking about X bar, the mean of the sample. We're talking about S, which is the standard deviation of the sample. So we can calculate those things, but those statistics themselves have distributions. And why do we care if the statistics, X bar and S, have distributions? Well, ultimately, we're interested in knowing what a confidence interval might be. So if we can calculate the mean of our sample, what's a 95% confidence interval surrounding that mean? And then we can compare other values. So we compare two samples, do those confidence intervals intersect or not? Are they statistically significantly different or not? Those are kind of the basic things that we can do with it. We get into hypothesis testing and tests of significance, comparisons of means, and we'll talk about that on Thursday. So today, our first learning objective is to compare and contrast the distributions of observations and then the distributions of the means of a sample of those observations. So ultimately, I should probably have written that as population. Population. So we have some underlying population, and then we have a sample of that population. And then we'll be looking at the distribution of X bar when we know the population variance, so when we know sigma, and then we'll be looking at X bar when we don't know that population variance, when we only know S, the standard deviation of our sample. We will then define and explore the student's T distribution. You may have heard this. So if you took stats in high school, you know, this is probably the stuff that you covered. Right? So it took us a long time to get here. The student's T distribution, which is the distribution of X bar when we have a standard deviation S from our sample. And that follows the student's T distribution. And then finally, we'll define and explore the chi-square distribution. We talked about this before with the goodness of fit test. The chi-square distribution also describes the distribution of the sample variance, or this kind of metric of the sample variance. And with that, we can compare variances. We can compare a variance from our sample with some population variance and say, is the variance different? Usually we're interested in the mean value or comparing something with the mean value, but we can also do these tests with variance. Okay. And I'll just take a poll. Did you guys take stats in high school? Did you do, yes, no, okay. So thumbs up for yes. Thumbs down for no. So maybe half of you guys did this. I didn't take stats in high school either. I'm kind of sad I didn't, because it took me a really long time to eventually learn it. In fact, it took a PhD, but you guys are so lucky you get it here. I did take it in college. I don't remember anything from stats in college, which I hope is not the case for you guys. But I'll call you up in a couple years and find out. All right. So let's talk about the sampling statistic distribution. Okay, and again, sampling statistic is a statistic of a sample. In this case, we're talking about X bars. We're talking about the mean of the sample first. So X is just our observations. And so X is a random variable. Say X follows a normal distribution. It has a population mean and a population sigma. So there's some population out there that's representing the distribution of observations. Okay. Note that mu and sigma are population parameters. Parameters, that's an important part. And we're comparing parameters and statistics. So statistics are things like X bar and S. Parameters are representing the population, mu and sigma. So if X bar is the mean of our sample, and we have size n of X, well, we know how to calculate X bar, right? So X bar is going to be equal to 1 over n sum of xi. So for I equals 1 to n. Okay, we've all calculated a mean before, no big deal. Now, the distribution, so say we got that population, and we could do a simulation of this, right? We could do, and maybe that's what we'll do in our project, our kind of like final project for this, is you've got your underlying distribution of X. You take a sample, say 30. We'll take a sample of 30, so n equals 30. We'll calculate the mean. Then if we were to repeat those samples and say take 1,000 samples of 30 and take the mean, well, the mean, the distribution of X bar is going to follow a normal distribution, but it's not going to be the same distribution. It's going to have a mean of mu, right? That makes sense. The mean of the means is going to be the mean. You follow? If we're going to take the mean of a distribution with mean mu, well, that distribution is going to be centered around the same mean. Okay. But it's going to have a different standard deviation. That standard deviation is going to be sigma over square root of n. And sigma over square root of n is called our standard error. And standard error is based on sample size. So we're just dividing the standard deviation of that population, that underlying population, by the square root of our sample. So what does this tell us? Well, it tells us that if this black curve is our distribution of X, the original thing that we're sampling, the distribution of X bar in purple is going to be narrower because it has a smaller standard deviation. So the original standard deviation is sigma. If we divide it by n, and as n increases, as we get a larger and larger sample, then the distribution of X bar is actually going to be much narrower and a lower standard deviation. So we'll just note here that sigma is greater than sigma over square root of n, and that the kind of variability or the spread of our X bar, of our sample mean, is less than the underlying distribution. And we talked about the central limit theorem earlier in class. Can anyone restate the central limit theorem for me? I'm gonna look at my friend Justin because he's on top of my screen.
Trying to think back to that.
So the central limit theorem basically says if we take any distribution and we take a sample of it, we take the mean of that sample, the central limit distribution, or central limit theorem tells us what is the distribution going to be of that mean if the sample size is a certain size. what it says is the distribution of the means is always going to be a normal distribution or approximately a normal distribution. That's why we always are using normal distributions, right? Because they kind of, from a theory standpoint, represent the distributions of means of anything. So regardless of the distribution of x, so x could follow a normal distribution, a log normal distribution, it could be a binomial distribution, an exponential distribution. If we take a sample of that distribution, and as long as that sample is greater than or equal to 30, we take the mean of that sample and do that 1,000 times, the distribution of x is always going to follow some normal distribution. And it'll have a mean of either mu or x bar, and it'll have a standard deviation of sigma over square root of n. What we can also say is if we want to normalize and calculate the kind of just the z statistics here. So if we do x bar minus mu up top, and then we do sigma over square root over n on the bottom, that's going to follow a normal distribution with mean 0 and standard deviation 1. So now we can basically calculate a z-score for a mean value. And this is where this test of significance come in. So I'll just walk you through what that would look like. Well, actually, we'll get into the t distribution, and then we'll get an example of that. So often we don't know the population variance or mean, right? We just have a sample, and we don't have any other data. Where would you get a population standard deviation? Well, maybe so an example could be, actually I have an example at the end here, but medical data, right? So maybe we're interested in the resting heart rates of a certain set of athletes. And I've got a sample from athletes, say I'm going to sample the CMU basketball teams. Okay, so I got a sample of resting heart rates from, maybe whatever, 40 athletes. Then I can compare that to the national average. And so the study, maybe there's some medical database and they have thousands and thousands of samples of college athletes. So I could treat that huge database as my population mean, their standard deviation. And then I could say, okay, is my sample, are they different from that? Are they greater than or less than? Is the variance the same or is it different? So that's where these kind of tests come in, and that's what we're going to talk about on Thursday. But typically maybe we have a situation where we don't have that huge database or some theoretical mean and standard deviation to compare to. In which case, these pretty typical situations, we have a small sample size. So we can estimate our x bar mean, or sample mean, and we can estimate x. So x bar again is equal just to the sum of our x values over n, and then s, our standard deviation, is going to be equal to the square root of 1 over n, and the sum of the differences between our observations and the mean squared. So this is our s, this is our standard deviation, or sample standard deviation. Okay, well now, because we don't know the population standard deviation, we have S instead of sigma, we have a different distribution here. Before we had X following a normal distribution with this mean and this standard deviation, that standard error, those are standard deviation. Now X follows a different distribution, and this is called the T distribution. And in the video, they talked about where this came from. So it's called student's t-test or student's t-distribution. And student was the pseudonym of this, we'll call it industrial statistician, or he worked at what's the beer in Ireland that they make? I'm blanking on the name right now. Help me out here, guys. We drink it on St. Patrick's Day.
Was it Guinness?
Guinness. He worked at Guinness back in the day. I think this was may have been 1800s, maybe it was the 1900s. Yeah, I think they mentioned it in the video. And, you know, when you're making beer in a factory, you got to have quality control. You got to make sure that concentrations and specific gravities and bitterness are all within certain tolerances, right? And student knew that he didn't have population parameters to deal with. So how do you figure out if your, you know, the beer that you're testing from a small sample size is normal, is not normal, is kind of out of control? Meaning, I kind of like that phrase, out of control, because it's beyond some standard deviation of the mean. Well, he knew that he couldn't assume a normal distribution because that's just not how the data worked with small sample sizes. So he came up with the t-distribution, and the PDF for that t-distribution, it looks a lot like a normal distribution. It's symmetrical, but instead of, it's also, it becomes a function. You have a third parameter. You have the mean, the standard deviation, and then the degrees of freedom. And the degrees of freedom are a function of n, the number of samples you have. And that degrees of freedom influences the shape or kind of the spread of that t-distribution. So for our t-statistic, this is very familiar. Our t-statistic is just x bar minus mu s over square root of n. So instead of sigma, it's s. And this particular statistic follows a t-distribution with n minus 1 degrees of freedom. The degrees of freedom just simply refers to the sample size in this case. So take a look at that.
So then for that equation, like the x bar minus mu over like the s over square root of n. So for the n in there, would we use the regular n, so the number of samples, or would we use like n minus 1?
Yeah, so that's how you would. So this is very similar to calculating the z-score for something. In this case, we're calculating the t-score.
Okay.
And then when you go to the n minus 1 comes into play when you plot the PDF or calculate some probability associated with the PDF.
Okay.
So if you look at, and we'll get into, I'll introduce this code, and then we'll look at how you work with this thing. So when n goes to infinity, the t-distribution becomes the normal distribution. So when we have an infinite sample size. So as the sample size increases, we get closer and closer to the normal distribution. But for smaller sample sizes, so say n equals 7, degrees of freedom f is just n minus 1, right? It would be n equals 3. Degrees of freedom is equal to n minus 1, which is 2. The curve kind of starts to flatten and spread out. And so for a normal distribution, if we compare it to a t-distribution with a smaller sample size, we kind of get a bigger variance, and we get these fatter tails right here. So we get more probability of seeing an observation farther away from the mean.
Wait, can you say that again? So the less samples we have, the farther away we get from the true.
Yeah.
Mean.
The idea is, if we can think about it this way, if we want to compare, say we have a mean value that we say, okay, our beer coming out of this process has this specific gravity because of all the malt that we put into it. And we want to make sure that we're within tolerance of this, within plus or minus 2 standard deviations or something like that. So the way to do that then would say, okay, well, how many samples do I have? All right, well, I have 10 samples. So now I have 9 degrees of freedom, so n minus 1. So I can plot my t distribution here. And if I just had those 10 samples, then say my distribution curve kind of looks like this. So it's got a pretty fat tail. If I want to calculate how far of an extreme value I need away from the mean, such that I can say it's statistically significantly different from the mean, then I have to go much farther out into the tails to get to, say, I'm going to calculate the 95% probability or something like that. So I have to go much farther out into the tails to get that additional probability, and I have a much more extreme value than if I had a larger sample size. So my larger sample size will give me a tail that kind of descends more quickly, and they don't have to have such an extreme value to say that something's different or not. So it just comes down to the area under the curve and how far away you have to go, kind of away from zero in this case, to get a value of t calculated up here. Remember, t is going to be the difference between your sample mean and the overall mean that you're interested in comparing to. So for a smaller sample size, this t value, so we'll just say say I want to do a 95% confidence interval, just an upper value. So t.95, if we can look at the book real quick. That's going to be a bigger value for a smaller sample size than if we had a larger sample size. So let's take a look at the book real quick. We got a table here for t. I think it's table A3. Okay. So table A3, critical values of the t distribution for confidence level 1 minus alpha. And we were not talking about significance tests yet, but alpha refers to a test of significance. Typically, we set alpha to be 0.05. It's arbitrary, but it just says that something is different if there's a 95% probability. 1 minus alpha is 0.95. So degrees of freedom again. So if my sample size was 10, I have 9 degrees of freedom. My t value that I need to know at 0.95. So this means that 0.95 of the probability or area under the curve falls up to that value of t. And that critical t value is going to be 0.18. But if I doubled my sample size to 20, now I have 19 degrees of freedom. Well, I can have a less extreme t value. That t value becomes 0.17. And what that translates to, because if we look at how we calculate a t-score, that translates to a mean value that's not as far away, a sample mean, x bar, that's not as drastically different from the population mean that we're interested in comparing it to. And I can draw that out for you a little bit differently. So what I'm drawing here is just the two different t distributions that are a function of the sample size, as well as our mean and our standard deviation. So here would be my critical t value that I would have to compare for a 95% difference or significance level. And then my t value over here would probably be, this would be t 0.95 for 9 degrees of freedom. This is 19 degrees of freedom. And so that then translates to how big of a different value of the sample mean do I need to have to say it is actually different at the 95% confidence level from a population mean.
So then that value in the back, like the 1.8 or 1.9, whatever it was, you would just plug that straight in for t, and then you could find like your x bar. Is that how
Yeah. So you could say, okay, what value do I need for x bar what value do I need to exceed to say that it's actually different from mu, from the population mean?
Okay.
Yeah. Or you could alternatively just say, here's the value that I have for my sample. Let's calculate the t-score and compare it to that critical value from that table. And so all this is doing is we have 0.95 area underneath that part of the curve, and then 0.95 area under that part of the curve. So it takes, you have to go farther down the curve to get to that 95% area. Okay, so I think I covered why we care about the distribution of X bar of the sample mean, because we can calculate confidence intervals. What does that mean? We'll talk about that on Thursday. I just want to introduce other concepts now, and then we'll get into actually applying it. And then we can also compare means and stuff like that together. So here's that example of resting heart rates. I was just kind of searching for some real world example that we could talk about. And say we did a sample of CMU's basketball players. I don't know how many of you guys there are, but I chose 40. And we got a mean value of 61 beats per minute and a sample standard deviation of 5.2. Okay, well, we looked at the NCAA stats. They did a medical study. I'm making these numbers up. And we got a mean of 65 beats per minute for all college basketball players. Big sample. Well, so we'll call that mu. So now with this information, we can calculate a 95% confidence interval of our beats per minute and say, okay, well, what does that mean? Are we different or not? What's the kind of certainty? That's also kind of uncertainty, right? What's the certainty or uncertainty around our mean? Also, is X bar significantly different from mu? Do we have stronger hearts over here in Grand Junction? My guess is yes, but we could actually find out. So we'll carry that calculation out on Thursday. All right, so the last topic, and I'm going to give this a real short treatment that we have to cover, is the distribution of the sample variance. This is kind of a less common thing to use or to be interested in, but I'll just introduce it here. So here's our sample variance, so S squared. That makes me realize I might have given you the wrong equation up here. Oh, no, we're good. Okay. So sample variance, S squared. Come on, little focus there. There we go. We've calculated this before, and 1 over n minus 1, sum of the differences between the observations and the mean squared. To get the standard deviation, we just take the square root of that. Just as we said that X bar, the sample mean, follows either a normal distribution or a t-distribution, depending if we know the population variance or not. S follows, in this case, a chi-square distribution. And you can follow that kind of logic and derivation in the book. So S follows a chi, the sample variance, actually, sorry, that's S squared. S squared follows a chi distribution with n minus 1 degrees of freedom. So the chi-square distribution is kind of like the t-distribution except for the sample variance. So we can do a very similar test as I just outlined. We can say, okay, let's calculate this. It's called the C score, right? So instead of the Z score or the T score, now we have the C score. And the C score is n minus 1 S squared over sigma squared. And so this is where we can say, okay, well, here's some population variance. Is our sample variance different from that or not? So we can calculate a critical value for C, which is associated with some cumulative probability, just as we did before, the T 0.95, we can calculate the C 0.95 based on the chi-square distribution. And then compare that to our C value. So what does that look like? Well, here's the chi-square distribution. Again, it's a function of degrees of freedom, n minus 1. And just to go throw some numbers out there, say we know that there's some manufacturing process that produces certain kind of steel beam, and we're going to measure the number of fractures in the steel beam, and it's got a variance. The population overall from this process, based on years and years of data, is 9. So that's the variance, the population variance. And we just got a shipment of 41 beams and did our analysis, and we got a sample variance of 14.1. So is our variance, do we have more variability in these fracture numbers than what's coming out of the factory in general? Is our sample variance significantly different from the population variance? So we calculate our C score, which is just n minus 1 sample variance over population variance. We get a number. And the question becomes, okay, this number is going to fall somewhere on this chi-square distribution. It's somewhere out on the tails. Is that number more extreme or bigger than the value of C associated with a cumulative probability of 0.95? For alpha is equal to 0.05. So we can go to the chi-square distribution. It's in your book again. Or you can do it in R. So let's look for chi-square distribution to this table A4. There we go. Okay. So table A4, very similar to the table we just saw for the T distribution. We have degrees of freedom, so this is our sample size. And then we have our p-value. So if we're just interested in 95% difference, then we can say, okay, degrees of freedom. So in this case, we have 41 samples, so we have 40 degrees of freedom. And then our critical C value is about 55.8. Oh, in this case, they were doing a bit of a larger number, but that doesn't matter. So you could we'll talk about one-sided versus two-sided tests on Thursday, but this number comes from a two-sided test. All right, so we get that critical value. In this case, it was 59, 57, something like that. So here's our critical value right here. And this says that 0.975 of our probability of our area under that distribution comes before it. And here's our actual test statistic that we calculate right here from 62.5 from our sample variance. So now we can say, well, our C score is bigger than the critical value. And so we can say that our sample variance is significantly different from our population variance. We got problems. We got to send that order back. So very analogous to the T test, just a different way of calculating it in a different distribution. And I noted here that this is how we do it in R. So this is P for probability, chi-square, so CHISQ. We put in the significance level that we want, or the probability that we want, and then we put in the degrees of freedom, and it'll spit out this score. All right, guys, that's what I got for today. I've got a homework assignment posted. It's kind of mostly based off of what you guys saw in the videos and just this little overview today. And then for Thursday, we'll have 2 more videos. So one is related to significance testing and confidence intervals and I think the other one's comparison to means. So that's going to be the topic for Thursday. And in the book, we're going to read section 6.3 and 6.4, testing of hypotheses and confidence intervals. So make sure you skim through that stuff before class and check those videos out.
Hey Joel, what was the table? We got that C value for the 97% confidence.
What's the table?
Yeah.
Table A4 for the chi-square distribution
Okay.
right here. And then for the T distribution, it's table A3.
Okay. Cool.
And then I just forgot to go over that quiz real quick. We can do that together. All right, so should be a good review of what we just talked about. The distribution of sample means with known population variance should follow the normal distribution regardless of the distribution of the original data from which the sample was collected. Is that true or false? Thumbs up for true, thumbs down for true, right? So that's the central limit theorem right there. The standard deviation of the means of many samples from a population will always be larger than the standard deviation of the population itself. False. Good job. All right. And we know that because we're dividing by a square root of n, right? Whenever we're looking at the sample, the standard deviation of the sample mean, it's going to be less than that original standard deviation of the population. Okay, if we have a sample size n, we calculate a sample mean from that sample size, the standard deviation. The distribution of the sample means with unknown population variance estimated by S will follow what kind of distribution? Make the letter with your fingers. T. Okay. This would be chi-squared distribution. So I think is the next question. The distribution of variance of a sample follows what kind of distribution? Chi-squared. Okay. Yay. All right, guys. Thanks for being here. I will be on again in about 15 for any questions. I'm posting the homework assignment in a minute to homework 8 due in a week.
Joel,